So how do we get from vibrato to FM synthesis and thence to quantized frequency modulation or chaotic FM? Well, let's set up a bona fide FM synth first. This was merely vibrato being demonstrated. Make some slight alterations. So we have our modulating oscillator, and it's going to be scaled, multiplied by a depth value. And we could just control the frequency of that oscillator independently, but in FM synthesis we don't do that, and the reasons will be explained very briefly in a moment. In FM synthesis what we do is we scale the center frequency by a ratio, and that then becomes the frequency of the modulator, so that the center frequency and the modulating oscillator frequency are in a relationship, they're interdependent. So I'll copy and paste my line object, that will control the ratio. So we need some comments here now to clarify things. Center frequency, modulating oscillator ratio, and we need a control over the depth, and we could control the depth independently. Again, in FM synthesis we don't normally do this. We can do it. It's open to interpretation. The standard FM synthesis algorithm, we use the frequency of the modulating oscillator as a scalar for the depth. That is to say that all parameters are dependent upon the center frequency. The center frequency is multiplied by a ratio to give the frequency of the modulating oscillator, and that frequency, i.e. the frequency of the modulating oscillator, is itself scaled by what's referred to as an index, which dictates the brightness of the timbre, or the number of sidebands and the amplitude thereof. I'll set up a little scope so we can visualize what's happening here. Then that value is becomes the depth. In common parlance, the effect depth, the depth of the vibrato. And the whole thing is added to the center frequency. We should now hear the classic FM synth sound. That's our center frequency. There's a pure tone because there's no modulation happening. Let's set a modulating ratio of 1 and slowly raise the index. If you hold shift while scrolling in a number box, you can do it in fractions. As that increases, so too does the brightness. And if I shift scroll on the modulating, or I can type in 0.01, we should hear vibrato. So we can get back to our vibrato state if we need to, but we don't, because we're doing FM synthesis, which is audio rate modulation. Now there's a couple of handy little things I want to do. I want to be able to visualize what's going on to better explain how this FM algorithm works. And we're going to use a frequency spectrum or spectrograph. And there are a number of ways of getting hold of that tool. We can go to the help menu and in PDL2org or per data, open the, I think it's the help browser, scroll down to audio tutorials and zip all the way down to patch E01, spectrum. But we'll do it the boring manual way. File open, and in Linux, certainly anyway, I need to be in the user library. Which I've just lost. Okay, user library. Cancel, start again. Let's go to my Explorer, into my operating system. User is down here. Lib, scroll down to pdl2org, which is there, and in the folder called extra. No, it's not extra, it's doc. Audio examples. EO1. Where are you? EO1 spectrum. Open that. I'm going to just grab some handy little things here. So edit the patch. I'm going to grab this table. I want that. Tab right. And I also want the important thing, PDFFT. Control copy. Put those in my patch. Take the output from our final amplitude scalar here, send it into the FFT patch. I also want another metro. Control 1 metro 50 and a toggle to start it. And this will give us the frequency spectrum of the output. I'll not go into detail. Oh, sorry. I'll not go into detail of what that is or how it works. We can see and hear what's going on now. Vibrato around a center frequency. Set the index to 0. Put the modulating ratio slightly higher. Raise the index. Shift, click, drag. You see what we mean by sidebands. Oh dear, that jumped quite a lot. Yeah, one thing I like to do with the mod ratio and index is reduce them by a factor of 10. So Control 1, multiply tilde 0.1. It gives us finer grained control over those parameters. Control copy, verify. Oh, don't you dare. And he goes where? He goes there. No, he doesn't. I forgot about that. If you have multiple objects selected, click and drag to connect and they'll all connect. All the objects that are highlighted. So center frequency, mod ratio of 0.5. Raise the index. That's 0.05 actually. So the magnitude of the sidebands changes as I raise and lower the index, and the position and number of sidebands changes when I change the mod ratio and the index. And the reason we enforce a relationship between the modulating oscillator's frequency and its depth is so that when we change the center frequency, the logarithmic relationship between the center frequency and the sidebands is unchanged. That is to say, the character of the timbre doesn't change. And this is because when Chowning first invented FM synthesis, the main goal was computationally inexpensive recreation of acoustic instruments. And in acoustic instruments, we see this behavior that as pitch rises, brightness increases somewhat. So as we raise the center frequency, the index rises as well. And so too does the perceived brightness. But the underlying timbre is fixed by the relationship between the center frequency and the modulating oscillator's frequency. Yeah, a little too much explanation there. Maybe a glimpse into how limited my understanding is. Oh, nice and nasty. But now we're going to get even nastier by turning this simple FM synth into a quantized frequency modulation synth, or chaotic synth. And the key to doing that lies here. The output of the modulating oscillator. This is the modulator. This is the carrier. And this is where the FM magic happens, at this plus tilt. So I'm going to delete that and insert an object called samp hold tilt. And sample hold is a triggered oscillator. It stores its input and only outputs that input when it receives a greater than 0 value. Commonly from a phaser, but it could be from a low frequency noise oscillator or some other type of LFO. A phaser outputs a ramp between 0 and 1. And that will be our trigger. And let's just Control copy. Let's just set the frequency of that trigger independently, first of all, to see what it sounds like. Well, the phaser frequency, the trigger frequency is 0, so samp hold is outputting nothing. It's outputting 0, so I'm just hearing a pure tone. And we can see that we're just getting a pure tone. Let's shift drag. So the sample and hold oscillator is being triggered 1.75 times at 1.75 hertz, and it's arguably the classic sample and hold sound, that robotic 1950s computer sound. And again, in FM synthesis, the fun starts when the trigger starts to get up into the audio rate range, so faster than 20 hertz. Ooh. That's nice. And a little proviso in FM synthesis, and particularly chaotic FM synthesis, is that our final output doesn't do any harm. In fact, it's a safety measure, is to include a low-pass filter around about 2 kilohertz. And that value will change depending on age and listening environment, how sensitive your ears are. Okay, now we can listen to that. And the reason for that is because you can get very, very high frequency fold over, and we want to protect against that. So we're tapering off around about 1800 hertz. You might want to set it at 2800 hertz or 5000 hertz. So let's listen again. Now I'm going to change the center frequency, and the nature of this chaotic oscillation will change as the center frequency changes. And it becomes chaotic. If I change the modulating oscillator ratio, the character of the output changes as well. So we can use our little ratio trick. I'm going to use the frequency of the modulating oscillator multiplied by its own ratio. Grab that, control copy, put it over there, verify, and that dictates the frequency of the triggering phaser. Just make things a little clearer. That's not mod ratio, that is trigger ratio, or trigger frequency ratio. Let's have a listen. Now if I change the center frequency, the timbral characteristics of the output stay largely the same. If I change the modulating ratio, or the mod ratio, character is the same, but the oscillation, the timbral oscillations, speed up and slow down. So that would be a nice control to use for our FSRs. Index is depth. Subjectively, it's the brightness of the chaos. Let's change the sample hold frequency trigger. And things are still chaotic, so I'm going to change that ratio scalar to hundredths instead of tenths, and it lets us surf through. Some nice formants in there. So let's quickly get some interaction going here. What do we like to control? I can set the index and the trigger frequency ratio manually. I'd like to control the center frequency and the modulating ratio. So we need to work out a range. Let's go between, say, 50 and 1000 hertz. That's quite easily done. Remember from our FSRs, we're getting 0 to 255. So I use the expression object. Inside expression, we have to stipulate whether we're using a float, an integer, or a signal vector. So $F1 for $float1. What are we going to do with it? I'm going to multiply it by, so multiply by 50. Yeah, that's more like it. And add 50. And now, instead of using the PD interface, I can use my FSR. It's a little much. Let's change that somewhat to, we'll multiply it by 20 and add 100. And use another expression object, Control copy, verify for the ratio. And we're going to change that to, we want it to go between, well, let's see. It's 0 to 100. So we can simply Control E, multiply it by 0.5. Let's kill the audio there for a second so I can hear myself think. Multiply by 0.5. I'm just eyeballing this, really. Might be a bit much, but let's see. So the modulating ratio is 0 at the minute. That's FSR number 1. Let's see what FSR 2 introduces. Get some vocal formants in there, and then we can get extreme noise. Fat bass sound in there somewhere as well. Arguably, those ranges are a little high. So we'll multiply FSR 1 by 10 and add 200, and we'll scale FSR 2 by 0.25. Let's have a listen to that. A little more predictable control. So that's 2 DIY FSRs, a breadboard Arduino, COM port object in pure data, and some chaotic FM synthesis. That's enough for today, I think. Next video, I'll use the same hardware, but I'll use Supercollider, and we will do QFM synthesis and maybe a fat bass or something, I don't know, maybe some granulation. Only time will tell.